The broadcast is now starting. All attendees are in listen-only mode.
Hi, everyone. We're just giving it another minute. We have 200 people expected. We're up to 150. We will be sending the handout later, but also notice there is a questions tab. You will not be able to speak during this presentation, but you are able to write any questions you want in that questions tab. They will be answered during the webinar or in a follow-up email. You can also, after this webinar is over, you can send an email to the webinar at dep.nyc.gov with any questions, and we will follow up with you. So to begin, here's Erin Morey.
Thank you, Oscar. Good afternoon, everyone. Welcome to today's webinar on the New York City Department of Environmental Protection's, or DEP's, Citywide Parcel-Based Impervious Area Study. As Oscar said, my name is Erin Morey, and I am Director of Demand Management and Resilience Policy in the Bureau of Environmental Planning and Analysis at DEP, and I'm very pleased to present this webinar today. Before we get started, here are a couple housekeeping items. This webinar is being recorded. All participants are muted, as Oscar noted. If you have questions throughout the webinar, again, please feel free to type them in the questions box, and all questions will be answered at the end of the webinar as time allows. And finally, as we are working from home, internet is not always reliable. So if the webinar abruptly cuts out, please bear with us as we reconnect as quickly as possible. Today's webinar will start with an overview of the study's objectives and goals. From there, I will present an overview of the study findings, and we will wrap up today's presentation with a summary and next steps. Again, as time allows, we will conclude today's webinar with a question and answer session with DEP and ARUP. And with that, before moving on to the next slide, I would like to take this opportunity to acknowledge the ARUP project team, particularly Vincent Lee, Project Director, and Roland Martin, Project Manager, for their contributions to this study. I would also like to acknowledge the DEP project team for all their hard work and contributions, including Carolina Rybika Kotsiak, Alan Cohn, Melissa Enoch, Greg Mays, and also Ben Huff, formerly DEP and now with City Planning. Also, we would like to acknowledge Pinar Balsi, Assistant Commissioner of DEP's Bureau of Environmental Planning and Analysis, for her guidance. The objective of DEP's Citywide Parcel-Based Impervious Area Study is to generate a geographic information system land cover layer that displays citywide pervious and impervious area at the parcel level. This land cover layer includes imperviousness and perviousness for parcels only, not the right-of-way like roads and sidewalks. This is the first time that a parcel level land cover GIS layer was generated for New York City. It's an exciting and important milestone, certainly, and we are very pleased to be able to share the results with you today. One goal of the study is to expand and improve upon the analysis that informed the 2010 New York City Green Infrastructure Plan. The enhanced methodology used for this study, which will be described in the upcoming slides, plus updated technology and data inputs, resulted in improved resolution than what was achieved for the Green Infrastructure Plan. A second goal of the study is to inform and support citywide planning efforts, projects, and programs, and to apply the parcel-based impervious area GIS layer to ongoing stormwater planning, resiliency planning, and other initiatives. We will conclude the webinar with some thoughts on how this data can be applied. DEP's study is an 18-month analysis led by DEP's Bureau of Environmental Planning and Analysis and concludes in July 2020. The project team began the study with data compilation. All existing data was compiled, reviewed, and analyzed to determine suitability for the study. Since the parcel-based land cover layer is a derivative of these data sets, data compilation was a critical step. Overall, the data sets reviewed and used for this study are relevant to the time they were collected and achieve geographic coverage of the study area. Specific data sets used for this study will be discussed in the coming slides. From there, the citywide parcel-based impervious area GIS layer was developed. An object-oriented, segment-based mapping approach was used, taking vector and raster GIS data as inputs for the overall process, which will be described in greater detail. The GIS layer was delivered in packages to DEP borough by borough. Staten Island was the first package produced and delivered since it was expected to be the least complex in terms of land cover due to lower density and open fields and parks. During production of Staten Island, opportunities for workflow improvement were identified and applied to subsequent packages. It is also worth noting that due to size constraints, each borough is a separate geodatabase with 3 feature classes. The GIS layer development process was extremely detailed and time-intensive, and it is worth noting that this webinar provides only a very high-level and simplified summary of that process. Additionally, the project team also documented the methodology and business rules used to create the layer, the QA/QC methods implemented during development. An example of a business rule is that when a boat was encountered in the water, it was manually classified as water instead of the material of the boat, like metal or wood. Next, the project team developed a maintenance plan. The maintenance plan contains step-by-step instructions for updating the parcel-based GIS layer and will be used by DEP to periodically update the layer when source vector data sets are updated. Changes to the source raster data used for the study would require rerunning the process steps or basically redoing the study. Changes to the vector data set used, however, would only require rerunning cleanup and generating an updated version of the layer. In addition to producing this parcel-based impervious area GIS layer, the project team applied the layer to an analysis, specifically an analysis to determine the degree of change in imperviousness citywide between 2010 and 2019 and the reasons for those changes, like improved data quality and land development. This is one example of how the impervious area GIS layer can be applied, and we will discuss other potential applications at the end of this webinar. As mentioned, all source data sets used to develop the parcel-based impervious area GIS layer were analyzed and determined to be suitable for the study. Samples of the first 5 source data sets listed are pictured on this slide. Specifically, 4 core data sets were used. First, 2018 orthographic imagery, which is high-resolution aerial imagery, flown between April and May 2018 at a half-foot resolution. Second, 2017 LiDAR intensity and LiDAR digital elevation model, or DEM, flown between March and May 2017. Third, 2016 planimetrics from the New York City Department of Information Technology and Telecommunications, or DOIT, planimetric vector data set captured from 2014 New York statewide flyover aerial imagery. And fourth, the 2018 Map Pluto vector data set. An additional data set used to develop the GIS layer was the 2018 building footprints data from the DOIT buildings vector data set. Following data compilation and review, the project team continued with developing the parcel-based impervious area GIS layer, beginning with the land cover classification process. For this study, remote sensing was used to classify parcel surfaces in the city. Remote sensing is the science of obtaining information about objects or areas from a distance from aircraft, satellites, and handheld devices. For example, remote sensing was used to differentiate between grass and concrete. Since grass is pervious and concrete is impervious, remote sensing enabled defensible classifications of perviousness. In addition to capturing the visible spectrum, like red, green, and blue light, remote sensing often provides other bands of data, such as near infrared. Remote sensing enabled the project team to identify a broader range of land classifications, such as telling the difference between grass and artificial turf. These surface types have different levels of perviousness, so it was helpful to be able to separate them for this study. The project team identified a total of 19 land cover classes citywide, and each land cover was then assigned one of 3 levels of imperviousness: impervious, semi-pervious, and pervious. Those 19 classes are listed on this slide in order of most impervious with metal, rubber, and wood to most pervious with sand, grass, and bush. Each land cover class was also assigned a C value. A C value is a runoff coefficient between 0 and 1 and represents the ratio of rainwater that becomes runoff. Land cover classes are considered impervious when almost all rainwater that falls on those surfaces becomes runoff. Land cover classes that absorb rainwater and prevent it from becoming runoff are considered pervious. And finally, in the middle, land cover classes that absorb some rainwater but also contribute some runoff are considered semi-pervious. The C values used in this study are consistent with DEP's 2012 guidelines for the design and construction of stormwater management systems and best practices in other cities. You may notice that open water is not assigned a level of imperviousness, and this is because this land use is not a contributor to stormwater runoff on land, but rather a receiver of runoff. For this study, open water is considered any water segment that is contiguous with an ocean or major river. Open water was not clipped from the layer because piers, which are considered a parcel and were classified in the study, can sometimes extend out into open water. It is important to note that open water, while included in the study, was excluded from the percent imperviousness calculation for each parcel. However, water, which is defined as small streams, lakes, and ponds, is a separate land cover class and is included in the percent imperviousness calculation for each parcel. And finally, you may also notice that some of the land cover classes, like solar panels, pools, water, and trees, were not assigned a C value. This is because the engineering publications with guidance on C values that the project team reviewed did not have values for these features. However, the project team did categorize these as impervious or pervious based on practice experience. This next slide provides a very high-level summary, of the project team's process of developing the citywide impervious area GIS layer, which took many months. An object-oriented segment-based mapping approach was used, using the previously mentioned vector and raster data as inputs, including orthoimagery and LiDAR for the following process. First, during segmentation, the orthoimagery, including red, green, blue, near-infrared bands, and the LiDAR data sets, including the digital elevation model and intensity, were combined into a single data set. An algorithm was used to divide contiguous areas with similar surface characteristics, like elevation, into small segments. Second, during training site selection, the project team classified just over 1% of segments by visually inspecting them against the 2018 orthoimagery and determining what land cover class each segment represents, like grass, concrete, and roof. The project team then trained a computer model to automatically classify the land cover classes for the remaining 99% of segments based on that 1% of segments that were classified manually. These computer classified segments were then manually checked and cleaned by the project team as part of supervised classification. Finally, during reclassification, the classes, like grass, concrete, and roof, were assigned a level of imperviousness. So again, pervious, semi-pervious, impervious, or open water, consistent with the land cover classification process presented on the previous slide. After that, the data was clipped to map Pluto parcel data and was converted to a percentage, providing a value of imperviousness, semi-perviousness, imperviousness for each parcel citywide. Before presenting the imperviousness percentages for each borough, I would first like to discuss accuracy and these percentages and how this study defines overall classification accuracy and measure of confidence. So classification accuracy is a standard method for defining how accurately a computer model is performing based on manually defined accuracy set. The accuracy set was chosen and assigned a class manually prior to the classification. They are used to compare against the computer model output to assess the accuracy of the result. Put another way, this is a measure of how accurately the computer model automatically classified those 99% of segments. 85% is a widely accepted value for classification accuracy in remote sensing, and as you will see shortly, each borough achieved a classification accuracy of at least 85% in this study. To explain another way, a classification accuracy in the table of 0 means that the algorithm or computer model never matched the surface type that the project team manually assigned. A classification accuracy of 100% means that the computer model always matched the surface that the project team manually assigned. Moving on to measure of confidence, this is a measurement that was specifically developed for this study to help define the quality of the completed land cover GIS layer against an independently assessed land cover layer, which was manually digitized by a hydrologist. This was a way to check the work of the computer model. An independent hydrologist manually categorized surfaces within a representative subsample of parcels in each borough, and this was compared to the computer model's classification. Measure of confidence represents the percent of surface area where the computer model and the hydrologist were in agreement. Again, to explain another way, shown in this table, a 0% measure of confidence means that the completed GIS layer never matched the surface type that the independent hydrologist assigned. A 100% measure of confidence means the completed layer always matched the surface type assigned by the hydrologist. This slide concludes the very high-level description of the methodology and process the project team used to develop the parcel-based impervious area GIS layer. The next slides show the actual layer and levels of imperviousness at the borough level. For Manhattan, an overall classification accuracy of 85.86% was achieved, and a measure of confidence of 92.35% was achieved. Manhattan is 63.009% impervious, 14.39% pervious, 1.67% semi-pervious, and 20.85% is open water. The percent imperviousness calculation used for all parcels and boroughs is also indicated at the bottom of this slide. The calculation is total impervious cover divided by total parcel area, excluding open water, multiplied by 100 equals total percent impervious. Land cover percentage is ordered from largest to smallest on the left hand of your screen. In Manhattan, the top 3 land cover types, roofs, asphalt, and open water, comprise 73.5% of the borough. The other 16 classes comprise the remaining 26.5% of the borough. For the Bronx, an overall classification accuracy of 89.22% was achieved, and a measure of confidence of 88.82% was achieved. The Bronx is 57.58% impervious, 30.41% pervious, 3.75% semi-pervious, and open water is 8.25%. In terms of land cover in the Bronx, the top 3 land cover types, asphalt, roofs, and trees, comprise 59.05% of the borough. The other 16 classes comprise the remaining 40.95%. For Brooklyn, An overall classification accuracy of 86.90% was achieved, and a measure of confidence of 92.01% was achieved. Brooklyn is 60.86% impervious, 21% pervious, 3% semi-pervious, and 15.13% is open water. The top three land cover types in Brooklyn, roof, asphalt, and open water, comprise 56.94% of the borough. The remaining 16 classes comprise 43.06% of the borough. Moving on to Queens, overall classification accuracy achieved is 88.05% and a measure of confidence of 96.36%. Queens is 57.39% impervious, 27.24% pervious, 2.15% semi-pervious, and 13.22% is open water. Again, in terms of land cover, for Queens, the top three land cover types are asphalt, roofs, and grass, and that comprises 53.71% of the borough. The remaining classes comprise the remaining 46.29%. And finally, Staten Island. For Staten Island, an overall classification accuracy of 85.65% was achieved, and a measure of confidence of 87.3% was achieved. Staten Island is 38% impervious, 45.98% pervious, 6.29% semi-pervious, and 9.73% open water. In terms of land cover in Staten Island, the top three land cover types, trees, grass, and asphalt, comprise 55.49% of the borough. The remaining 16 classes comprise the remaining 45.51% of Staten Island. These next slides highlight an example of how the parcel-based impervious area GIS layer can be applied to a specific analysis. In this example, the project team applied the GIS layer to compare pervious change between 2010 and 2019. Specifically, the intent of this analysis is to determine the degree of change in perviousness citywide between 2010 and 2019, and the reasons for those changes, like improved data quality and land development. 8 reasons for change in imperviousness and perviousness between 2010 and 2019 were identified. The intent was to identify broad trends to generally describe the reasons for gains and losses in perviousness. Beginning with improved data and methodology. This includes increased resolution between 2010 and 2019, methodology improvements, correction of incorrectly identified surfaces in 2010, and other errors found in 2010. For land cover changes, this includes new developments and other significant changes in land cover between 2008, which was the imagery date for the 2010 data set, and then 2018, which was the imagery date for the 2019 impervious area GIS layer. For tree canopies were on in 2010, meaning that land with a tree canopy was considered pervious, even if the parcel's land cover was concrete and impervious. For the purposes of this study, canopy was removed in that parcels with a canopy were classified not by the canopy, but by the land cover beneath the canopy. Regarding bare soil, gravel, and synthetic turf, these 3 categories were classified as impervious in 2010. But for this study, these are classified as semi-pervious, which is consistent with other cities. Regarding natural features includes coastal areas, wetlands, and other areas that were subject to change due to natural reasons between 2010 and 2019. Regarding green roofs and playgrounds, these categories account for green roofs and playgrounds installed or removed since 2010. And finally, category 8 unknown, accounts for any data not classified in one of the previous categories, including locations where the data provided no clear indication of what had changed. While this category cannot be eliminated entirely without ground surveys and ground truthing, which was not part of this study, the study ensures that at least 85% of each borough's area was assigned a category other than unknown. This analysis indicates that the net pervious area change since 2010 is a decrease of 0.12 square miles, or 76.8 acres, which is about a 0.1% decrease. The table on this slide provides a breakdown of that net pervious area change. The first column provides the reason for that change. The second column provides an accounting of the pervious to impervious change from 2010 to 2019. And the third column provides the inverse, an accounting of the impervious to pervious change from 2010 to 2019. Broadly speaking, 23.65 square miles of pervious area were lost between 2010 and 2019, while 23.53 square miles of pervious area were gained between 2010 and 2019. So the math is 23.65 square miles minus the 23.53 square miles equals approximately a decrease of the 0.12 square miles as indicated on this slide. Looking at the table, 91% of the pervious loss citywide was due to improved data and methodology. This means that 21.59 square miles were incorrectly classified as pervious in the 2010 data and were reclassified correctly as impervious in 2019. On the other hand, 61% of the pervious gain citywide was due to improved data and methodology. This means that 14.42 square miles were incorrectly classified as impervious in 2010 and were classified correctly as pervious in 2019. Thus, the improved data and methodology in 2019 versus 2010 cuts both ways. Sometimes it means that area was incorrectly classified as pervious, and sometimes it means that area was incorrectly classified as impervious in 2010. The table further describes the reason for change citywide, and while the upcoming slides indicate that individual boroughs show visible changes and discernible trends in this analysis, these changes broadly cancel out citywide. The net pervious area change since 2010 in Manhattan is 0.95 square miles, or 608 acres, which is a 31% increase. Looking at the table, improved data and methodology accounted for 77% loss in perviousness and 53% gain in perviousness. Notably, 4% of Manhattan's gain in perviousness is attributable to green roofs, as indicated on this slide. These green roofs were installed at Javits Center, Mother Clara Bus Depot, U.S. Federal Courthouse, Langone Hospital, Hilton Midtown, 75 Rockefeller Plaza, and 245 and 255 Greenwich Street. Other notable land cover changes occurred on Randall's Island and Ward's Island, where there was an extensive gain of pervious land cover, plus new green space at the Cornell Tech development. You may notice that Central Park and Riverside Park appear green, indicating that they were classified as impervious in 2010. This is due in part to the low resolution of the 2010 data. The 2010 data correctly identified pathways in both parks as impervious, but it also identified the pathways as being much larger than they actually are, so the surrounding areas are shown as green or pervious area gains. Generally, you may also notice that some boroughs, especially Queens and Staten Island, will appear much more red than green, indicating that there are significantly greater losses of perviousness than what actually occurred. This is due in part to the improved resolution of the 2019 GIS layer, which can yield mixed results as previously mentioned. Specifically, again, areas that were incorrectly classified as impervious in 2010 were revealed as pervious in 2019, and vice versa. Additionally, the project team encountered something called the edge effect in this study, where in raster GIS analysis, the edge of the raster shortens the number of cells being evaluated, causing a bias in the resulting cells along the edge. In terms of this study, this translates to the appearance of more red area or imperviousness than what there actually is. The net pervious area change since 2010 in the Bronx is 1.9 square miles, or 1,216 acres, which is a 15.1% increase. Looking at the table, improved data and methodology accounted for 88% loss in perviousness and 71% gain in perviousness. The primary cause for pervious area gains in the Bronx is smaller post-industrial developments, specifically, as shown on this slide, the New Horizon Court residential development, building demolitions on Rikers Island, and green space additions at Co-op City added to the increase in perviousness since 2010, as did the increased green space as part of the development of the new Yankee Stadium. The net pervious area change since 2010 in Brooklyn is 2.6 square miles, or 1,664 acres, which is an 18% increase. Looking at the table, improved data and methodology accounted for 87% loss in perviousness and 70% gain in perviousness. One of the causes for pervious area gains in Brooklyn is natural areas, specifically the Jamaica Bay wetlands, which were not identified as pervious in 2010. The primary cause for pervious area gains in Brooklyn were developments with green spaces, including the 5th Street Pier, South 9th Street Pier, Gateway Center Mall expansion, the South Brooklyn Marine Terminal, and finally Brooklyn Bridge Park. The net pervious area change since 2010 in Queens is 0.24 square miles, or 153.6 acres, which is a 0.7% increase. Looking at the table, improved data and methodology accounted for 94% loss in perviousness and 57% gain in perviousness. For example, it is worth noting that the Jacob Reese Park parking lot, which is one of the largest parking lots in the city, was incorrectly classified as entirely pervious in 2010, but was correctly classified as entirely impervious for this analysis. Notably, the inclusion of bare soil, gravel, and synthetic turf as semi-pervious in 2019 also accounted for 24% gains in perviousness in Queens. As just presented, Manhattan, the Bronx, Brooklyn, and Queens all had a net pervious area increase since 2010. Staten Island, on the other hand, experienced a net decrease in pervious area since 2010. Specifically, the net pervious area change since 2010 in Staten Island is a loss of 5.8 square miles, or 3,712 acres, which is a 15.7% decrease. Looking at the table, improved data and methodology accounted for 92% loss in perviousness and 45% gain in perviousness. The primary cause of pervious loss in Staten Island was new development, including the Tottenville residential development, the townhouse development in Clifton, and the Bloomfield West Shore development, which for this analysis was the single largest loss of perviousness citywide. Small lot level developments not shown on the map were also significant and contributed to the overall loss in perviousness. In summary, the parcel level land cover GIS layer generated by this study is the first of its kind for New York City. The layer is based on a robust methodology, updated data, and enhanced technology, making it an important policy and planning tool. The table on this slide summarizes the impervious area GIS layer, specifically the percent impervious, semi-pervious, and pervious at the borough level. Additionally, the parcel level land cover GIS layer can be broadly applied. Applications include, but are not limited to, supporting models for estimating flooding and other climate change impacts, correlating imperviousness with other metrics, including heat and surface temperature, erosion, socioeconomics, and population and density trends, illustrating the effectiveness of green infrastructure at managing stormwater and imperviousness, and finally, supporting a one water or integrated approach to managing the city's water resources. And with that, I will turn it over to Alan Cohn, Managing Director of Integrated Water Management at DEP, to further discuss DEP's integrated water management portfolio and the role of this study in expanding that portfolio.
Thank you, Erin. I'll also use this opportunity to remind people to please submit your questions if you haven't already, so that we can answer them towards the end of this call. The Water Research Foundation defines One Water as an integrated planning and implementation approach to managing finite water resources for long-term resiliency and reliability, meeting both community and ecosystem needs. I'm going to discuss how measuring and managing imperviousness area is part of a One Water approach in New York City. Impervious area contributes to stormwater runoff, which affects water quality in New York Harbor and contributes to flooding. Measuring impervious area allows us to understand opportunities to better manage stormwater. A One Water approach considers not only how to reduce the impacts of that stormwater runoff, but how to optimize stormwater as a resource. Next slide, please. The first example of this approach is DEP's Green Infrastructure Program. Green infrastructure diverts runoff from impervious areas into rain gardens like the ones depicted here, which then allows rainwater to infiltrate back into the ground, mimicking the natural water cycle. Mapping helps identify where there are opportunities to manage impervious area with green infrastructure. Green infrastructure not only absorbs stormwater, but offers multiple ecosystem co-benefits, such as urban heat island reduction. Next slide, please. Another opportunity for stormwater management is storage. That is, creating space for large volumes of runoff below ground in storage tanks or above ground in detention basins. Storage is especially important in large rain events when the ground may become quickly saturated. These large events are also known as cloudbursts. Cloudbursts are typically short, intense events that we may experience during a summer thunderstorm and which can lead to flash flooding. Building on the success of the Green Infrastructure Program, we've initiated a cloudburst management pilot program to develop high-capacity solutions for these types of events. One of our first pilot projects is a partnership with the New York City Housing Authority at the South Jamaica houses. There, we've identified several areas to create opportunities for stormwater to collect in large volumes by using existing open space. We plan to excavate several shallow grassy areas to allow water to pool before it ultimately collects in storage tanks below a basketball court. The basketball court will also be lowered so that in a heavy rain event, when the grassy areas and below ground storage tanks are filled with water, the court itself will temporarily flood. The next slide illustrates what these areas will look like in one of these events. By measuring how impervious area and other factors contribute to flooding, we will be able to identify areas of New York City that may experience flooding during future cloudburst events and where we can deploy cloudburst solutions for temporarily storing water. Next slide, please. Our next examples are truly illustrations of One Water as they optimize benefits across the water cycle from drinking water to wastewater. New York City parks already offer great benefits for managing stormwater. Even here, however, there are One Water opportunities. Several water bodies in our parks partially rely on drinking water to help maintain water levels. During heavy rain events, however, the excess runoff can spill into combined sewer systems, contributing to combined sewer overflows. In some cases, parks draw down the water levels when they know rain is coming in order to create additional capacity. DEP is partnering with the Central Park Conservancy to recover some of that excess water that is typically discharged to sewers and recirculate it, which offsets the amount of potable water that is typically used to refill water bodies during dry periods. This recirculation project is projected to save an average of 830,000 gallons of water per day and reduce approximately 4 million gallons per year of combined sewer overflow to the East River. DEP is also partnering with the Prospect Park Alliance to replace a potable water valve to reduce the flow of water, thereby creating capacity in the water bodies to absorb additional stormwater runoff. This project is estimated to save an average of 800,000 gallons per day of potable water and reduce approximately 12 million gallons per year of combined sewer overflow to New York Bay. Next slide, please. Our final One Water example is on-site water reuse, wherein individual buildings or groups of buildings collect and recycle water that would otherwise be discharged to a sewer system and use it to offset drinking water that is used for non-potable purposes, such as flushing toilets, cooling, and even laundry. Rainwater is just one of the potential sources for reuse and requires less treatment compared with the other sources shown here. Next slide, please. DEP has funded several examples of water reuse and recirculation throughout New York City. The Green Infrastructure Grant Program funded projects such as the Forest House and related companies' projects, where rainwater is collected and reused. In the top left example, we're irrigating plants in a greenhouse. The grant program also funded a project at the Local 1 Plumbers Union to reuse rainwater for in-building purposes. Our water demand management program also helped fund a recirculation system at the Brooklyn Botanic Garden, which opened last year. We also worked with the New York City Fire Department to create a system to collect and reuse drinking water that is used to calibrate the equipment on New York City's fire trucks. Clearly, there are many opportunities for managing stormwater runoff from impervious areas, and we will continue to support new innovation in New York City's One Water approach. By measuring imperviousness, we can continue to identify these opportunities and measure the impacts of our interventions. With that, I'll turn it back over to Erin to conclude the presentation and answer your questions.
Erin, you're muted. Erin, we still can't hear you.
Okay, how about while we're waiting for Aaron to get back, Alan, you want to see if you could maybe answer some of these questions? Now,
Can you hear me?
now we can.
Okay, sorry about that. Not sure what happened there. But anyway, thanks, Aaron. We'll get to the question. I did want to conclude on this final slide, just to show what's going to be uploaded to open data. So we will plan to provide this data on open data, and Clear is going to include 3 feature classes for each borough, which are shown on this slide. So the impervious area per parcel, the percent impervious area per parcel, and the land cover classification per parcel. While I was muted, I was saying, thank you to Alan for his presentation, and we look forward to seeing how you plan to utilize and incorporate this parcel level GIS layer into your work as well. So a couple of questions that I've seen pop up, happy to start to answer those. One of them is, will the recording of the presentation be made available? The answer is yes. We're working on the technical backend to make that available to you, so we will keep you posted on that. Same for the deck today as well. Another question was, why was the right-of-way excluded from this analysis? And the reason why we excluded the right-of-way from this analysis or from the parcel level study is because it is just that, it's a parcel level study only. And because the New York City Department of Information Technology and Telecommunications, or DEP, provides a citywide planimetric layer, which already enables that simple classification of highway surface types and covers the majority of right-of-way locations. So since remote sensing is a time-consuming process, it was deemed unnecessary to perform analysis on right-of-way locations. Another question came up on open water and why that was not clipped out of the study. So we went back and forth on that, and again, open water was not assigned a level of imperviousness because again, it's a receiver of runoff and not a contributor. However, we didn't clip it from the layer because piers, which are considered a parcel and were classified as part of the study, can sometimes extend out into open water. So we wanted to make sure that we covered that. I'm not seeing necessarily other questions. I do apologize if I'm missing those. Oscar, perhaps you can see if there's other questions that came in.
The last question I see is, did you do this one from Chrissy Remind? Can you speak further to your methodology for the C-value score?
Sure. Happy to turn that over actually to Arup. Roland Martin or Vincent Lee, are you available to answer the question on C-values?
Yeah, we can. I can help contribute to that. So what we did was, I mean, with the premise of the study being on evaluating this for stormwater runoff and the linkage to impervious coverage, what we did was we reviewed different C values. And if anyone who practices engineering, you know that whenever you go through any publications and guidelines regarding C runoff coefficients, they vary, right? There's some variation between them. So we, as Aaron mentioned, we cited the New York City guideline, DEP's guidelines, and then we also took a look at other ones as well. And then from there, we started to classify the numbers between 0 and 0.91 or 95, just to see which ones would be considered impervious and semi-impervious and pervious. So the obvious ones, asphalt roofs, those would be impervious. The grass, obviously would be pervious. And then we started to compare the different C values that we would find for all of the other, 18 or 17 land cover land cover types across the city. see where we thought it would best fall. So it was a combination of using our practical experience in terms of engineering hydrology, and then also a review and a pretty elaborate matrix of different C values that we studied across different publications.
Thank you, Vincent. Oscar, are there other questions?
Yeah, you just gotta scroll down. So the next one was what software was used to do the remote sensing analysis? Did you use Envy or other software?
Vincent, would you step in for that?
Yes, we used PCI Geomatica.
Okay. How did the 2014-2018 date range for your source data sets affect the analysis?
Vincent?
I mean, I think in terms of the data sources that we used for the study, what Aaron presented on was, a lot of the primary sources that we used. Mind you, the list of sources that we initially studied were quite robust. So where we did find differences in the ones that we eventually settled on, with the varying years, it was a combination of the remote sensing and us checking through the tiles and through the training sets. And then it was also us in our QA/QC process of evaluating, the imagery with the different data sets, whether it was LiDAR and the planimetrics. There was a pretty much more detailed methodology that we went through to be able to, resolve some of the differences. But in the end, we didn't find too many differences in those different years.
Thank you, Vincent.
Okay, we got two more came up. Did you conduct analysis that compares permeability from 2010 to 2019 by neighborhood? What about lots with certain land use or building topology? If not, would it be possible to conduct that data? Perhaps Pluto, yeah.
Yeah, that's a great question. We did not look at it at the neighborhood level, but again, when this GIS layer becomes available on open data with these three feature classes shown on the screen, that's exactly the type of analysis that you'd be able to do. Because I believe that some of the 2010 data that informed the 2010 Green Infrastructure Plan is available. We also obviously have other data available on open data that can lend itself to that analysis, but we did not do that as part of the study.
Okay, next one is how much stationarity is there in the 2019 result? That is, do you expect the climate change will affect these results, and if how so?
What was the first part of that question? I'm sorry, Oscar.
I'll just send it on Teams to you.
Okay. In terms of, I can just speak broadly about climate change, and we might have to follow up over email about this particular question. But I think climate change is a great example, as we mentioned, that this layer has utility for looking at climate change impacts, and certainly this is a snapshot in time of 2019, but using data from past years as well. So I think, to answer your question, we can take this conversation offline, but in general, again, it's a snapshot in time. So in terms of how we see climate change potentially impacting, what we see in this study remains to be seen. And with that, we are at time at 2:30, so I'm going to advance to the last slide, which has our contact information, which is impervious map at dep.nyc.gov. Please feel free to reach out with your questions. And we thank you for your time, attention, and robust questions today, and apologies for the technical difficulties. But that concludes our webinar for today. Thank you again, and take care and stay safe. Oh, and I'm told actually that you cannot see the screen that I'm seeing. So again, that contact info is Impervious Map. It's IMPERVIOUS map at DEP.nyc.gov. And this presentation will be emailed to all participants, and it will have that contact information. Again, apologies for the technical problems, and thank you for your time.